This mechanism we designed basically. We took the influence of how like a rowboat rows through the water.
Yeah.
So we have these mechanisms right here that are just a hole cut through a board, and then a spoke going through the center with a slot. So this allows the rotation of the wing, maintains its upright stability, but at the same time allows this to rotate and this not to rotate. So as this flaps, this changes the angle of attack with cyclical motion, like that. It changes the wingtip and angle of attack. And this, in concept, works very well, but we couldn't find a power delivery system that would work with it. So the motors that would provide enough torque to actually move the wings were too heavy to fly. So we had to abandon this model for something simpler.
Did it fly?
No, this one didn't fly. So then we have this one. And this one, I'm going to flip it upside down because it works a little bit better. But this is a mechanism that actually changes the angle of the crankshaft and thus changes the angle of attack of the wings. And as you can see, the cyclical motion of the wingtip is actually preserved on this model. It's not moving straight up and down. This creates the type of, like, imagine a dolphin diving through the water. That's the type of effect we wanted with the wings carving through the air. Unfortunately, because of the manufacturing constraints of this front mechanism right here, we couldn't get an accurate enough model that would provide smooth transition between each phase of the flapping. So because of that, our power delivery system, again, was not enough to overcome the friction and the mechanical constraints of the system. Again, we had to refine our model. Now, the next model we had was this four-wing model right here. And this one actually has a motor on it. This one works extremely well as a glider. It's very powerful and flies very fast, but it provides no lift by itself. This one doesn't have the type of vorticity that the next one I'm going to show you has.
Of the wing motion.
Yes, this is because of the wing motion.
Just simply flaps.
Yep, it just simply flaps up and down.
It's important to have like flapping and also rotate.
Right, because these aren't very free. The normal vorticity would be created in this area, but when the wing flaps shut, it just shoots all that air back out. So it doesn't give you the suction that lifts it into the air. So this works extremely well as a glider. If you throw this and turn it on, it's actually battery powered. That'll just go. It just flies. It works great. But our original project constraint said that we could not provide initial velocity on the butterfly. We had to let it go, and it had to move by itself. So then
Does it do that?
Yes, this one actually does. So when you crank it up right here, this actually changes the effective angle of attack. As you can see at the downbeat, the angle of attack 0. It's almost completely flat. Then up here, you have an inclined angle because it's attached to the back.
I see.
So this changes the angle of attack.
Now what makes it happen?
So we're powered by a rubber band on this one?
Yeah, but this one, the shape of the wing is a key.
Yeah, the shape of the wing, because it's malleable. So it's floppy. So as it flops back down, it goes up in a nice, slow, controlled motion, and then just goes flop back down. And that creates a vorticity above the wing.
How about this? This one is just like folds around here. The wing. No?
Yeah.
It's not to remain rigid and flat.
Yeah. This.
So it just gives like a concave zone.
It gives a little bit of a suction as it flops back down. Like it's in the same way you'd imagine a suction cup hitting a table.
The suction? Oh, okay.
Yeah. So we actually have on this video, we set up a smoke machine and used that as a wind tunnel. And you can see as it's flying that there keeps appearing a section of air above the wings that's empty, that sucks all the fog out of. This is because it's creating a section of vortices and eddies above the wing that creates a suction that creates a low pressure region. So this low pressure region is then not in equilibrium with the high pressure region that's under the wing, and it causes lift and lifts the mechanism. And we actually have a better view of this. We ran it through a filter.
Is this because of the change of the shape?
Yes. Because
if it remains flat,
as it goes up, when it starts to come back down like this, then it's like a suction cup when there's air going through it. So it goes up and then it snaps back down really quickly, and that creates like a whooshing motion. Same way if you moved your arm down in a pool and there was something floating next to you, it would actually swipe everything around above you because it creates those vortices. And if you want to look back here, we ran a filter on it, and you can really see how much air is being, like what the difference is. There's a lot of air that's being pulled down on each flap. The suction is creating a large section. Right here?
You see it? Oh, yeah.
So, and then we showed that if the wings aren't flapping, it does not glide, it just falls. So that was a low frequency test. Now with the prime optical, you see I pull my hand away really quickly because I don't want it to look like I'm throwing it. So I'm not throwing it. It just, boom, move away real quickly and it flies by itself. There's no initial velocity on this. And then we ran into the problem where it kept spinning. So we were like, we couldn't determine why it was spinning. And then it turns out it's because the way I was pulling my hand away was actually creating a vortex with my hand that was sucking the airfoils down, or not the airfoils,
so subtle?
membranes, and turning it. So in order to get these straight,
Can you actually use it to make it turn?
do you want me to? Oh, can I pull it like that?
I mean, in future, for example, you want to, instead of going straight,
If it was
just
flying
go
and I want
this?
like this next to it, it would turn.
Really?
Yeah. Because in the same way that this is very responsive to
Yeah.
the suction it creates here,
Yeah.
any nearby suction
Yeah.
will change it. We had to scrap so many videos of this flight pattern because it was even just the smallest bit breezy
Yeah.
would just knock this all around and interrupt the flight pattern. So this in still air works great.
Yeah. You know, this one is, what is the frame rate of this picture?
Do you know what the frame rate of the capture is for that video? That's at 0.25 speed.
Did you use a high-speed video?
I think it was just on our phones. We just used our phones as the video camera.
So you're not going to do this? Okay. I have high-speed video.
If you want us to, we can run it again.
Yeah.
We still have the smoke machine up in the mezzanine.
Yeah. Can you do that sometime?
Yeah.
Yeah. I don't
I'll
know.
email you. We'll set it up.
Yeah. Yeah. I'll bring the high-speed video.
Okay.
Yeah. If you don't mind. Yeah.
Not at all.
Oh, this is a good job.
Thank you.
Excellent. So that one is the final one.
This one
Yeah.
is the exact same as this one,
Yeah.
but Professor Bagchi just requested we had two models in case one of them broke during present.
Yeah.
So there's
Oh.
not much difference. The only difference is the tail shape. We wanted to see if it made a difference.
Yeah.
As long as it ends up being at about the same angle,
Yeah.
it doesn't really make a difference.
So this one actually, there's nothing here, but it just deforms by itself by the low pressure.
Yeah.
So the vortex is created at the top,
Yeah.
which actually reduces the pressure.
Yep.
So that's why it is actually. Wait a minute. This one is actually when you do it. Yeah. Is it possible to actually the actual butterflies pronate? When it's flopped, just like this. This is the angle.
Yeah.
Just instead of doing this, just moves, rotates the wing this way. Like if you like a bee, and then when it goes up, it just spinate like this, like this.
The actual wingtip motion of
Yeah.
the butterfly is a
Yeah.
figure eight, so
Yeah.
it's actually doing this
Yeah.
through the air.
Yeah.
But we
Yeah.
couldn't design a simple enough mechanism
Yeah.
to emulate that motion.
Okay.
So